Welcome to The Explainer. Today, we're diving into one of those hidden technologies that quite literally builds the world all around us. All right, here's what we're going to cover. We'll start with the big challenge in casting, then look at the hidden defects that cause so many headaches. After that, we'll get into a new way of seeing inside the process, how AI is giving it predictive power, and what all that means for making Foundry smarter and greener. And finally, we'll wrap up with what the future looks like. It's a heck of a journey, from an ancient art to a cutting-edge science. Okay, first step, casting's perfect challenge. We see and use aluminum every single day, but getting it just right, well, that's a whole other story. So think about it for a second. A fighter jet, an EV, your phone, what could they possibly have in common? Well, it turns out they all rely on this one manufacturing process, one that's been with us for thousands of years. But right now, it's taking this massive leap from, guesswork and intuition into a real, predictable science. And the answer is precision aluminum casting. I mean, this stuff is the unsung hero of our modern world. It's what allows engineers to create these complex, super strong, but incredibly lightweight shapes. Think about it. The delicate case of your phone, the tough chassis of a car, the intricate parts in a jet engine. It's all made possible by cast aluminum. It's literally everywhere you look. But here's the thing, and this is the catch that has driven engineers crazy for generations. It sounds simple enough, right? Melt some metal, pour it in a mold. But turning that chaotic liquid metal into a perfectly solid, flawless object, man, that is way, way harder than it looks. The whole name of the game is trying to tame that chaos. Which brings us right to the heart of the problem, the hidden defects. You could almost call them the silent killers of quality. Because as that metal cools down, a couple of major things can go wrong that can just completely ruin the part. So first up is something called gas porosity. The best way to think about this is like a can of soda. When aluminum is molten, it soaks up hydrogen from the air, just like soda holds onto carbonation. But as it cools and solidifies, it just can't hold all that gas anymore. So what happens? The gas forms these tiny little bubbles that get trapped inside the metal. And each one of those bubbles is a tiny weak spot. And then there's the other big one, shrinkage cavities. You see, when aluminum cools from a liquid to a solid, it actually shrinks. And if that cooling process isn't managed with just insane precision, that shrinking can literally pull the metal apart from the inside out. It creates these empty pockets or voids that are just disastrous for the strength of the final part. Okay, so how big of a deal are we talking about? Well, get this, 35%. According to the International Journal of Metal Casting, these two little problems, gas porosity and shrinkage, are the reason that more than a third of all aluminum castings get thrown out. I mean, just think about that. That's a staggering amount of wasted time, wasted energy, and wasted money. All right, so for the longest time, foundries were pretty much working in the dark. It was all based on experience, gut feelings, and a whole lot of trial and error. But that's finally changing. Now they're getting a new way of seeing, basically giving them superpowers. And this right here really shows you the night and day difference. The old way, casting blind. You've got a couple of temperature sensors, and the rest is just hoping for the best. It's like trying to find your way through a maze in the dark. But the new way, with fiber optic sensing, now you're casting with sight. You get this incredible real-time thermal map. It's data-driven, it's precise, it's like flipping on the lights. So how does it work? The big breakthrough is a technology called Rayleigh backscattering sensors. Just picture these super thin fiber optic cables, like threads of glass, embedded right into the casting mold itself. These fibers act like a complete nervous system for the mold. They're constantly sending back temperature data from thousands of different points with a crazy high resolution of just 0.65 millimeters. What you get is this beautiful, detailed, live heat map of exactly what's happening as the metal turns from liquid to solid. Okay, so being able to see inside the mold in real time, that was huge. That was step one. But the next step, well, this is where it gets really powerful. It's about moving from sight to foresight. It's not just seeing what's happening right now, but predicting what's going to happen. And that, of course, is where AI enters the picture. I mean, these new sensors are generating an insane amount of data, way more than any person or team could ever hope to analyze. So you feed all that rich thermal data into a machine learning model. You also feed it the results of past castings, the good ones and the bad ones. The AI just churns through it all, looking for these incredibly subtle patterns and connections that we would never, ever see on our own. So the process looks something like this. First, you feed the AI all that training data. Then the AI gets to work and builds its own predictive model. And finally, the magic part. You can give this system a brand new design and it'll tell you the probability of different defects showing up before you've poured a single drop of metal. This is the absolute game changer. You're not reacting to problems anymore, you're predicting them before they can even happen. And what this really creates is this incredible partnership between human engineers and the AI. It frees up the engineers to do what they do best: innovate, get creative, and solve the really tricky design challenges. Meanwhile, the AI acts as their super smart assistant, doing all the heavy lifting on the data side, predicting outcomes, and basically guiding them toward a perfect result. This whole idea comes together in what's called a digital twin. And it's exactly what it sounds like: a perfect virtual copy of the entire physical casting process. It's living, it's breathing, it's constantly being updated with that real-time sensor data. And with this digital twin, you can run thousands of simulations and experiments in the virtual world. You can tweak the design, change the temperature, try anything you want, and perfect the process without ever wasting a single drop of actual metal. It's amazing. So all this tech is cool, but what does it mean for the bigger picture? Well, it's making foundries way smarter and way greener. And the impact here is profound. There's this great quote from Warren Bennis that kind of sums it all up, even if it is a little funny. He said, "The factories of the future will have only two employees, a man and a dog. The man is there to feed the dog is there to stop the man from touching the machines." And yeah, it's a joke, but it gets at a real truth here. As these smart systems take over the complex number crunching and predicting, the human role changes. We become the strategists. The whole operation just gets smarter. And one of the biggest wins here is for sustainability, especially with recycling. Just look at this. Making brand new aluminum from raw materials takes a ton of energy. But recycling it uses up to 15 times less energy. That is an enormous difference and a massive opportunity to cut down on the environmental impact of manufacturing. So you might be asking, well, why weren't we just using more recycled aluminum before? And the answer is quality control. Scrap metal can have all sorts of impurities, which makes those defects we talked about even more likely. It was just too risky. But now, with sensors that see every detail and an AI that predicts problems, that risk just vanishes. Manufacturers can now confidently use up to 80% recycled scrap in their mix without worrying about quality. That's a huge step toward a real circular economy. So, let's bring it all home. The future is cast. We've moved from an art based on trial and error to a truly predictive science. So, what does that really mean? What happens now? Well, what we've really seen is this absolutely monumental shift. Aluminum casting, this process that's a cornerstone of how we build almost everything, has transformed. It's no longer a reactive art form, full of secrets and gut feelings. It's become a precise, data-driven, predictive science. We're not just making stuff anymore, we're understanding matter at a fundamental level as it's solidified. And this new level of control just blows the doors wide open for engineers and designers. Things that were too complex, too risky, too difficult to make before, they're suddenly on the table. And that leaves us with one last, really exciting question to think about. If we can now cast pretty much any shape perfectly every single time, what impossible things are we going to build tomorrow?